Why is zero potential theoretical in grounding? Imagine trying to keep a level surface perfectly flat while walking on a bumpy road. That's similar to what grounding systems attempt to do in electrical setups. In theory, we often talk about zero potential as if it's a fixed point, but in reality, it's more like a goal than an absolute. When engineers design grounding systems for power and renewable energy, they aim to create a common reference point for voltage. This helps protect equipment and people from electrical shocks. However, the Earth itself isn't a perfect conductor. It has resistance and impedance, which means it cannot absorb or supply unlimited current without some change in voltage. When current flows through a grounding conductor, voltage drops happen because of this resistance. This causes the ground potential to rise above zero, especially during faults or heavy load conditions. This rise in potential is called earth potential rise or ground potential rise. It's like the ground temporarily becoming slightly charged, which can be dangerous if not managed properly. Grounding systems include components like transformer neutrals and grounding electrodes. These parts also have their own impedance. For example, in systems where the neutral is directly connected to Earth, the source impedance from transformers and other equipment prevents the system from being a perfect zero impedance path. During faults, the current causes voltage variations in the grounding system, making the ground potential fluctuate. In electronic circuits and printed circuit boards, the ground plane is often treated as a zero voltage reference. But due to resistance in conductors and differences in ground references between interconnected devices, small voltage differences can occur. This means that what we call ground is often an approximation, not an absolute zero point. From a power distribution and protection standpoint, grounding is vital for safety. It helps limit transient overvoltages, allows fault currents to trip protective devices, and reduces shock hazards. But because of physical and electrical constraints, achieving a true zero potential is impossible. The resistance of the earth and grounding conductors always causes some voltage to be present. In summary, zero potential in grounding systems is a theoretical idea because the earth and grounding conductors have finite resistance. When current flows, voltage drops happen, and the ground potential can rise. Source and system impedances prevent a perfect zero impedance path. Electronic ground references can vary due to layout and connections. While engineers aim to keep the ground as close to zero as possible, absolute zero is just a concept, not a physical reality. Understanding this helps in designing safer, more reliable power systems and renewable energy setups.